So in this presentation we're going to cover networks. This is the basics of networking. We're going to go into more detail on certain elements of this in other videos, but for now let's get on with what we're going to cover in this. So the core issues related to computer networks. What are computer networks? Then we're going to go on to the types of networks and their characteristics and explain the topologies, and topology means the layout, the organization of different parts of devices and end devices in networks. So you're going to focus on local area networks. We're going to cover the other networks so you recognize them and you understand what the point of them is, but all your work is really going to be focused around local area networks. We're going to briefly go over home internet connections and discuss how that relates to business connections as well, because many businesses use the same kind of internet connection as home users, but obviously a lot faster. We're going to explain packet switching, discuss what that is and why we use it. That's just how current modern networks operate using packet switching. We'll go into what that means. The basic understanding of network protocols. So protocol is the agreed form of communication. That's just what a protocol is, and we're going to discuss how that works within networks. We're going to explain what a firewall is and what the role of a firewall is. You might have heard that term before. We'll go into a little bit more detail than you probably understand at the moment. Then we go into host names and IP addresses. That covers some of the network numbers, not network numbers, sorry, binary that we've covered in previous classes. And we'll also then discuss the domain name system on the internet. And then very briefly at the end we'll cover cloud computing. So, networking. A computer network, what is it? So, a collection of computing devices are connected in order to transfer data. So, this can be two laptops connected by one wire, that's a network, or this could be the internet, that's another network. So the internet is one massive, it's the biggest network there is. So that's the key thing. It can be the smallest, as in two devices, so that could be your two iPads communicating together using a wireless network just between the two iPads, or it could be between your smartphone and your laptop. That's a network. So the connections between computing devices can either be physical, a cable, an Ethernet cable, or maybe a fiber optic cable, or it could be wireless. So that could be Bluetooth, for instance. That would constitute a network if two devices are connected via Bluetooth. So let's understand what kind of things appear on a network. So any single hardware device that appears on a network is identified as a node. So that could be a computer, that could be a router, that could be a switch, that could be a modem. Any one of those individual devices, your phone is a node. If it's connected to the network, it is a node on a network. So in the same way, a host is any endpoint device. So a modem is not an endpoint device of a network, because that connects your laptop to the internet, or that connects your smartphone to the internet. Therefore, it's not an endpoint device. Your smartphone is an endpoint device, your iPad is an endpoint device, your laptop, your desktop computer, they are hosts. That is an endpoint device, therefore they are hosts. Whereas a modem, or a switch, or a router, and we'll go into what these are in this presentation, they are not hosts. So data transfer rate. So whenever we're discussing any kind of movement of data across a network, we're going to discuss how fast it travels, therefore we're going to discuss bandwidth. Okay, so how fast does that data move between one networking device and another, between one node and another node, or one host and another device? So when we're discussing that, we've discussed previously megabytes and kilobytes and those kind of things. When we're discussing size of files, we discuss it in bytes, but whenever we're discussing about transfer rate of data, we're talking about bits. Now you know the difference between a bit and a byte. A byte has 8 bits. Therefore, whenever we're talking about kilobits, we're talking about how many thousands of bits are moving. When we're talking about bytes, we're talking about how many bytes there are. Now, we never talk about bytes when we're talking about transfer of data. We always talk about bits. So computer networks generally have created this kind of model of a client-server model. Now, anytime you check your email, maybe you're checking your email on your phone will be the client, and it will be connecting to a server. Maybe that's a Exchange server when it's a corporate email or a school email, or maybe you're checking Google, Gmail. That is still checking a server. Okay, so the client is maybe your phone, and it connects to a server. So your phone requests email from a server, and the server responds with that data. That's the key thing. Servers serve, they respond to requests from clients. So protocol. So a protocol is a set of rules that defines how data is formatted and processed on a network. So how different devices interact for certain different requirements. Now, an email server will need to use different protocols when it's transferring email than a web server does, or maybe a file server does. Different services use different protocols, and you're going to learn a few of these protocols. We'll go through some of those protocols in this presentation today. That you'll need to generally understand the difference between them, and just remember the short form of those as well. So just some examples of servers. Now, there are many different types of server. We've just got here file server and web server. Now, you'll notice over on the right there's these icons. This is something called a Cisco icon. Now, you're going to be designing networks using lucidchart.com, and these icons are on Lucidchart, and you're going to be using these types of icons. Now, we'll go into it in more detail. We'll do a walkthrough on Lucidchart on how to design and draw a network, but I'm just introducing them, these icons to you, so you know you will be using these kind of things. So there are many, but we won't be using that many, probably 12 or something like that. And whenever you see these, now when you see these in an exam, or when you draw these in an exam, you do not have to be exactly they don't have to be exactly like this. You need to take some key elements, and probably the most important thing is you need to label them. That will be the most, if you're not sure what it looks like, you do need to at least label it and make sure that it is obvious what you're trying to describe. So if you're just describing a file server, draw a box, write file server next to it, just to make sure. So a file server just serves files to multiple users on a network. A web server provides web pages on a network, or more commonly on the internet. So the types of network. So as I said before, you're going to be focused mainly on local area networks. So the short form of that is LAN. So a LAN is a relatively small number of machines in a small area. Now, that might be two laptops connected together using a cable, an Ethernet cable. That might be your phone connected to your laptop using Bluetooth. That is a local area network. Just those two devices would constitute a local area network. The small number of machines doesn't kind of give you too much details of how big that gets up to. Now, in a school or a business environment, you might find hundreds, probably even thousands of computers in one building, or a number of close buildings. That would still constitute a local area network, and we'll discuss the kind of devices within that kind of network that would reduce the traffic on that. So we need to discuss topologies. Now, topologies is purely just how networks are laid out. What devices go into the network, how they are connected, that is a topology. So we're going to go through three different topologies: ring topology, star topology, and bus topology. And we're going to go through it looking at some diagrams of those. So on the left here we have ring topology, and it's fairly obvious what that looks like. It's a circle, and it goes, data moves in one way. So it starts here, moves to this one, moves to this one, moves to this one, keeps going round until it gets back to this one, and then they start transferring data again. So the downside of ring topology is it does go one way. Now you might see a ring topology in a slightly different way. The key is data moves one way, and if this happens, the whole network fails. As soon as one cable is broken or one connection is broken, the whole network fails. That's why generally we don't use ring topologies anymore. Now when you see these lines, so you'll be drawing these kind of diagrams. When you see these lines, these do indicate a physical connection. This indicates a type of transmission media. Now transmission media is a term you need to be aware of. When you consider media, you might think of television, maybe newspapers. Media in networking, whenever you're talking about media in networking, usually it's referred to as transmission media, but it might just be referred to as media. It's talking about connections between devices, whether that's a computer, whether that's a switch, or maybe a server. They're talking about connections. That connection might be physical, as in this diagram here, these solid lines between each thing. That indicates a solid connection. That could be Ethernet, coaxial, that could be fiber. We'll go through those in later. But you can also have wireless transmission media. So we haven't got any diagram here displaying that. I'll show that in another in the walkthrough with Lucidchart. But a transmission media can be wireless. Just bear that in mind. So that's on the left there. That's the ring topology. Generally not used. Do not use that for any diagram, any network designs you create. In the middle we have star topology. Now this is the most common topology that we use. The benefit of this, so data will travel between this one and this one. So I'll change that to a arrow. So data will move from this computer to this computer, this one to this one, this one to this one. And the benefit of this is if we lose this connection, if this media, transmission media breaks or gets disconnected, the whole network, the rest of the network still keeps working. This computer is disconnected, but the rest of the network can still work. So that's generally why we use the star topology. It's very efficient, and it's works well if certain parts of it break. On the right here we have bus topology. Again, if we have a connection that breaks here, in theory this side of the network can still connect, and this side of the network can still connect. So it's not as bad as a ring topology, but it's still not ideal in design. Now you will find you'll have elements of bus topology within your network. That's fine, but generally we should always be looking towards star topology as your choice of network design. So we've discussed local area network, which is LAN. We're just going to very briefly cover WAN and MAN. So wide area network is a WAN, a network that connects local area networks together over possibly large geographic distances. Now, the school has a LAN, the whole school has one LAN. Now, if we had a campus in Perth, for instance, we might want to connect and make that network appear to be part of our local network here. When we make that connection, that is a large enough distance to justify it becoming a wide area network. Because generally we would actually go out onto a public network, public broadband, and use some kind of fiber connection between this campus and another campus. Now it wouldn't be a direct connection, and we'll go into why that is in another tutorial, but it would constitute a wide area network. Now that's one example. The other most common example that you use all the time is the internet. The internet is a wide area network. It's the biggest wide area network there is. So bear that in mind when you're considering wide area networks. The internet is one. We're going to briefly discuss metropolitan area network, also known as MAN. Now we don't often come across this as such, but the most important reason why we're discussing it is because of WiMAX. You need to understand what WiMAX is. So generally, metropolitan area networks are created using WiMAX. Now WiMAX is not your average Wi-Fi. We will discuss that again in another video. We'll discuss the different kinds of wireless connections, such as Wi-Fi, such as cellular connections like 3G and 4G. WiMAX is slightly different to all of that. It's still wireless, it's very fast, and it can work over longer distances, quite large distances, and it can handle many devices connecting at once. So you need to remember that metropolitan area networks are generally used using WiMAX to connect. So that's generally a wireless connection used throughout a city would constitute a metropolitan area network and would generally use WiMAX. And the other thing you need to make a note of is, which I'm hoping you're doing as you go through this video, because you do not want to watch this video again, you need to remember or note down the 802.16. So this 802.16 standard, because it's a standard, is more commonly known as WiMAX, and you need to be able to interchange between. If I ask you a question about WiMAX, you need to be able to quote back to me, oh, it's the 802.16 standard. And if I say, what is the 802.16 standard, you need to quote back to me WiMAX. That's the kind of thing that will come up in an exam. So we're going to cover a few more 802.16. We're going to cover a few 802 numbers relating to Wi-Fi. We're not going to cover that right now. We'll cover that a little bit later. You just need to understand that these standards are created by the IEEE, which is the Institute of Electrical and Electronic Engineers. So it's a worldwide organisation that approves or gathers information and approves different standards. And I think that's all we need to cover on that. So we're just going to cover gateways. Now, we've got two icons here. We've got this icon here, also known as a router, and we'll cover what that means in a minute. But this icon here is also called a gateway. Now, as you see here, it has the router arrows. So this has arrows at the top, which kind of indicate that it's a router, and this does as well. And then it has this kind of arrowed sun thing in the middle, and kind of relates to a switch. Just bear in mind, you can use either one of these. The key to a gateway is any LAN that connects to another network needs a gateway. So all of these computers within this LAN need a gateway to connect to other networks. Individual computers generally are not able to connect to other networks without a gateway. Bear that in mind. Now, that gateway could be called a gateway, could be called a router. If it's at the edge of a network connecting to another network, it means that router is a gateway. Just please bear that in mind. So, very briefly, internet backbone. So there's a set of high-speed networks that carry internet traffic across the country and across the world. You'll generally be aware of Telstra. Telstra would be one of those companies, but there are many other companies in the world that do that. So the internet backbone, they're very fast using fiber optic cable. Now, because fiber optic travels at the speed of light, it means it's very fast and can handle very large bandwidth. When it gets more closer to in cities and in towns, they break out into internet service providers. So you'll be aware of internet service providers. Telstra is one still that deals with individual houses and businesses, but also companies like iiNet, Exetel, Westnet. You might be aware of some other ones. They are internet service providers, and they connect the final connection between your house and the internet. They provide those connections, and we'll cover what those connections are in a minute. We'll just very quickly go back to internet backbone, and we'll have a look at map and just see how that works. So on the left here, we can see a map of the major underwater internet connections throughout the world. So pretty much every part of the internet travels under the sea. That's how the different countries connect. So next time you kind of sitting checking your Gmail going, why is this running so slowly? Well, that could be because your connection is running from here all the way under here, all the way to somewhere in America, because your email server is actually could well be sitting in America. So it's not necessarily that your little brother's running a game on the computer and sucking up all the bandwidth of your internet connection. Actually, the whole of Australia could be trying to connect to America, and therefore that one pipe there or these few pipes here might actually be too small. So bear in mind, all of this is fibre optic running under the sea. When it gets more close to home, so this is the Telstra wholesale internet map. So this is the internet backbone that covers Australia by Telstra, specifically by Telstra. So they're the backbone, internet backbone, main internet backbone of Australia. And you can see that they have some very key core links. And then when they get into these cities, that's when most of the network's still controlled by Telstra, but other companies can lay their own networks, like Optus and iiNet. They lay their own network in the cities, and but also other companies, maybe like Westnet, Exetel, use other people's networks and resell those onto you. You're still using a Telstra network. So when you connect to the internet, you need something called a modem. Now, modem stands for modulator, demodulator. You need to make a note of that. Modulator, demodulator. And that means basically it converts analog to digital and digital to analog. Okay, that's a modem. That's how you sum up a modem. If you ever get asked what a modem does, it just converts analog to digital and digital to analog. That's what it does. So obviously your computer is data, it outputs data, it's all digital data, ones and zeros. Your phone line generally can't handle ones and zeros. So it needs to be transferred into an analog signal to be sent to the next part of the internet, the ISP connection, which is your local exchange, at which point that gets turned generally nowadays back into a digital signal and sent onto the internet. So phone modems generally aren't used anymore, very, very slow. More commonly is DSL modems and cable modems. Now you will probably be more aware of ADSL. Your home connection might be ADSL. So the A in the ADSL is asymmetrical digital subscriber line. So asymmetrical means basically that one direction is faster than the other. And generally in ADSL terms, the download speed is faster than the upload speed. That's generally what you'll find with ADSL. Cable modems again might often generally need to convert analog to digital and digital to analog. If you're fortunate enough to have NBN and fibre to your door, you do not need a modem because fibre is all digital. Therefore, you will just need a device that connects your network to fibre optic cable. Doesn't need to convert the data. It still needs a piece of hardware to connect to the internet, but it does not. It is not a modem. You would refer to it more commonly as a gateway, again, because your home network, regardless of whether it's a 10 or 15 digital devices or just your iPad connected to your ADSL wireless modem, that is still a local area network. Remember that any two devices, so your iPad connected to a modem router is a network because it's two devices connected. So when it connects to your router, when your local area network connects to the internet, it needs a router to connect. So at home, your ADSL modem, it is a modem, but it's also a router, which is a gateway at that point, and it's also a wireless access point and something called a DHCP server, which we're going to cover in a minute. Okay, so broadband generally is referred to as anything faster than 768 kilobits. Remember, whenever we were talking about speeds, we're talking about bits, not bytes. So a connection over 700 or 668 kilobits per second, because we're talking about per second because it's speed, would be classified as broadband. So pretty much all digital subscriber line connections and cable modem are classed as broadband. Even if sometimes they don't seem to operate at that speed, they're still classified as broadband. Okay, so now we move on to packet switching. Now, before we go into this, I just want to very briefly go over what the difference is and why we call packet switching packet switching. So down the bottom here, this is what would have been originally how the first telephone system worked, and it's called circuit switch network, or circuit switching. So when you picked up a phone, it would connect, your phone would connect to exchange, would connect to another exchange, would connect to another exchange, and then would connect to the final destination. And that connection would stay consistently the same until the phone call finishes. Okay, one path doesn't change throughout the whole thing. Now in packet switching, that's not how it works, and we're going to go into that now. So a packet is a unit of data sent across a network. One single piece of data. Now a web page is not one single piece of data. A web page, for instance, would be split into many packets, and each one of those packets would be sent across the network. To send packets across the network, you need routers, often also called gateways. So a router knows where things are meant to be going and forwards it on to its next, or its final destination, or its next point of its journey. So packet switching is how these packets are moved through a network. How do they get split into those little packets? How those packets are numbered? How they're directed to their final destination, and then how they're reassembled. So if we go back to the diagram, so when we send a message here, so Mr. Watson, come here, I need you. That was the original message that was transmitted in the first phone call ever made. The message here would be split into many parts, and then that would be transferred over this network. But each packet, the first packet would go to this router, and it might go to this router, but then it might go to this router, then it might go to this router, then that one. The second packet might go from this one to this one to this one, and then this one, which means the second packet actually took less time because it went through one, two, three routers and then got to its destination, whereas the first packet went to 1, 2, 3, 4 routers and then got to its destination. But the key is here, they all got to their destination. Now, if at any point any of this configuration broke, so for instance, if this transmission media here had a digger go through it, that doesn't stop the network working. The network still carries on working because the packets can go from this one to this one to this one to this one to this one, or it can go from this one to this one to this one to this one to its destination. So different parts of this network can break, or different, so these network transmission media can break, or these routers can break, certain parts of these routers can break, but things will still work. Now when you compare that to the circuit switch network, when you've made that connection, if this transmission breaks, or if this exchange breaks, the phone call finishes, ends and fails completely. And then a new connection has to be made if there is things available. That's the downside of a circuit switch network, and that's why packet switch network works with all modern networks now. So here's just another diagram of how packet switching works. So here's the original message. The message gets split into 3 different packets. Each packet is sent across the network, possibly over different pathways, and then they are received at the end, but they come in different order. Packet 2 comes first, then packet 3 comes, and then packet 1 comes at the very end, perhaps. Doesn't always work that way. But if it comes in like this, all that happens is the a gateway at the other end, receives those packets, knows it's going to receive 3 because the first packet comes in, which is packet number 2, and packet number 2 has information with it that says packet 2 is the second packet of 3 packets that are coming towards you now. So the gateway at this end is going, okay, I've got packet 2. Oh look, I've just received packet 3. I'm just waiting for packet 1. As soon as I've received that, I will push it onto its final destination and then display the message. So that's generally a very quick overview of how packet switching works and why we use it. And that's across every part of the modern networks now uses packet switching. So moving on, network protocols. So as mentioned before, protocols are just agreed standards of communication. And so because the internet, because networks are so large and have so many different devices, they need agreed protocols to communicate. Otherwise they're not going to know what to do. So when I go up to someone, like if I personally go up to someone and say hello and hold my hand out, that the protocol is the person at the other end who I'm approaching, they hold their hand out and say hello back, maybe ask how I am. This is a kind of protocol, and it's an agreed form of communication. Same with networks, it needs agreed forms of communication for things to work. So we're going to cover the protocol stack in more detail, but very briefly now, these kind of top level high level protocols sit on top. So SMTP, FTP, you'll probably be more aware of HTTP or HTTPS. We'll go through those in a minute. So they sit on top of something called TCP/IP. So Transmission Control Protocol and Internet Protocol. I think we'll cover this in more detail in another video, because these get a little bit more complex, and you need to understand the different stack of how these work together and the different layers within these. We'll also we'll in that same video we'll discuss the difference between TCP and UDP and the different uses for those. So yeah, we'll cover this in another video, but for now, just so you're aware, TCP, Transmission Control Protocol, breaks the messages into packets, hands them off to the IP software for delivery, and then orders and reassembles the packets at their destinations. The Transmission Control Protocol handles whether a message has been received correctly or not. The Internet Protocol is software that deals with the routing of packets through the maze of interconnected networks to their final destination, and it has a best attempt delivery, so it doesn't track whether it does actually work or not, and this is why we'll go into more detail of it in another video. Moving on, we'll ignore UDP and ping and traceroute for now. So we'll move on to protocols, and we'll discuss the different types of protocols. Now you need to learn some of these, and you need to be able to reference them back. So simple mail transfer protocol, so that's an agreed form of transferring email, basically. So electronic mail, whenever you see electronic mail, you're seeing email. And so when your email client, maybe it's on your phone, maybe it's on your iPad, maybe it's Outlook, maybe any of those, when it connects to your email server, it's using Simple Mail Transfer Protocol. Or when emails transfer between email servers, it's using Simple Mail Transfer Protocol to transfer that email. FTP is File Transfer Protocol, when files are being transferred over a network. So remember, when we're discussing these, now these can be traveling over the internet, which is a wide area network, or it could be traveling over your LAN, local area network. So just bear that in mind. These protocols work over any current network that you use. So that could be LAN, that could be a WAN. So File Transfer Protocol, FTP, transfers files from one computer to another. HTTP, Hypertext Transfer Protocol, transfers web documents over the network or over the internet. Now, that could be the web page, or it could be, or if it's the web page, it could also include elements that are within that web page, such as JPEGs or PNGs. So it's HTTP transfers the page, the HTML page. So HTML stands for hypertext markup language, but it also transfers the images that are displayed on that page. Perhaps it might even transfer some music or even possibly some video using HTTP as well. You might have also been aware of HTTPS, that stands for Hypertext Transfer Protocol Secure, or more commonly we say that as Secure Hypertext Transfer Protocol, even though the S comes at the end. Either way, it's a secure form of transferring data over a network, or more commonly over the internet. So for instance, your credit card details, you would not want to use a HTTP to transfer your credit card details, because remember, it's traveling over a number of gateways, and if any of those gateways pick up any of your information, they might try and steal your data. And there's other ways as well. But when you're transferring data that needs to be secure, such as credit card details, you always want to use HTTPS. Another protocol that's discussed on the in the ATAR course is Wireless Access Protocol. Now, Wireless Access Protocol is more commonly known as Wireless Application Protocol, and it's a little bit confusing because we don't generally use it anymore. When we had dumb phones, when we had dumb mobile phones, the old maybe flip phone, or the old Nokia phones, when they used internet, they used WAP, they used Wireless Application Protocol to transfer data, to transfer web pages. They did not use HTTP. So, but now we have smartphones and we use HTTP because we have browsers. Your iPad has Safari, your Android has Chrome. So they use HTTP now and HTTPS. So there's actually no reason to use WAP anymore. Really, the only reason you need to learn it is for two things. One, it's in the curriculum and they might ask you a question in the exam. And two, confusingly, there's another WAP that's used in networking, which is a wireless access point. Now, generally in networking, we would refer to this as an AP, or an access point. Now, any time you talk about an access point, you would generally infer that it's wireless. That's generally how you would discuss it. Again, we'll discuss how they work in network designs and network topologies when we get to that video. But for now, please make a note of this. Please make sure you remember this, that Wireless Access Protocol or Wireless Application Protocol is very different from Wireless Access Point, because they both have the WAP acronym, but they are very different. You need to be aware of that. So Wireless Access Protocol or Wireless Application Protocol is for dumb phones, dumb mobile phones, for transferring web pages over, but now we don't use it because we use smartphones that have Hypertext Transfer Protocol and Hypertext Transfer Protocol Secure. Okay, moving on. Here's just a few more protocols. There are many. We don't need to learn all of them. We will go as protocols come up that we need to know. We'll cover that, but basically the minimum you need to know is FTP, HTTP, HTTPS, SMTP, and WAP. It's useful. We're going to cover domain name service in a minute. That's quite an important one. Don't worry about the ports. Different protocols use different, often use different ports to communicate. In fact, they all use different ports to communicate. Some protocols can share ports, but it gets difficult to use multiple ports at the same time. Sorry, not multiple ports. The same port for different protocols at the same time. So generally, when a protocol is defined, it will always use the same port. So port 80 is generally always HTTP, and you would generally not change that. That would always be the same. Now, you don't have to set that, and hopefully those shouldn't come up, but it's useful to know that HTTP uses port 80, and it will always use port 80. Okay, firewalls. So a firewall is a gateway machine or software or both together that protects a network by filtering traffic in and out. Okay, so you don't want any network just getting into your network and having a look around and sending viruses in and malware and stealing your data out of it. So you need a firewall sitting at the edge of your LAN, at the edge of your. So generally it will be sitting at the gateway point. It won't be your gateway, but it will sit at that point, checking data in and checking data out, making sure the only data that gets in is data that has been requested by a computer on your network, and that is allowed. So the access control policy is a set of rules that govern what can be sent out of your network and also what can come in to your network as well. So firewalls, in this diagram you can see a firewall sitting here that is protecting the LAN. So this is the LAN, and then anything the other side of the firewall is the internet in this instance, and that just basically checks anything that's coming in and out. So now we're going to cover network addresses. So host name is a name, a natural name that's made up to identify a computer on the internet. So you can have host names within a LAN that aren't available on the internet, and we'll cover why they're not available on the internet in a minute. So just bear that in mind. Your local area network can have devices can have host names. They might not be accessible on the internet. However, host names that you will be aware of and easily recognise is google.com, scbc.wa.edu.au, webmail.scbc.wa.edu.au. These are all host names. Okay. Now, host names just link to an IP address. So really, the whole of the internet or the whole of the network, your local area network, and the rest of the networks in the world operate using IP addresses. So each networking device generally has an IP address, and that's how computers identify where things need to go. Okay, so it's an address. It's basically how do I get somewhere. Same as any normal like street address, an IP address is the same thing. It just is a number, just purely a number. So in this example here, 74.125.224.72 is actually google.com. So if you type that into a browser and hit return, you would actually end up at Google. Now, the reason we have host names is because we can't remember those numbers. That is not easy for us to remember. If I was a genius mathematician and numbers came easy to me, then maybe I would use this number to get to Google. But realistically, no one can do that. So that's why we have host names. Now we're going to cover how that works. So, this is very briefly. This is how IPv4. So we're going to learn about IPv4 and IPv6. IPv4 has these 4 numbers here to identify an IP address, and these all relate to binary. So 1, 2, 3, 4, 5, 6, 7, 8 bits. You know that makes a byte. The maximum number you can get to is 255. So in each of these numbers, it goes from 0 to 255, which is 256 in total. That's the total numbers you can have between. Those numbers make up an IP address. So the problem with that is there's a limit to how many numbers you can fit in those 4 digits. And that was fine when they first designed the internet. When they first designed networks and the internet, there wasn't that many devices on the internet. But recently, in the last decade or so, they've realized that, well, there's so many devices on the internet, there's not enough IPv4 numbers to go around. So the last block was given out in 2011. That was different companies get assigned blocks of IP addresses, and in 2011 that was the last time they assigned them because they had run out. There are no more IPv4 addresses available. So they're moving to an IPv6 format, which is 32 bits instead of 4. No, not 4. sorry, 32 bits. So 8, 8, 8 and 8 is 32 bits, sorry. So IPv4 is a 32-bit, but IPv6 is 32-bit organised into 4 groups of 8. Now you'll see this number down here. This is hexadecimal, and we'll cover that, or you might have covered that in another tutorial. We will cover that very briefly. You don't need to know it quite as well as binary, but you do need to grasp the concept. So binary is base 2, decimal is base 10, and hexadecimal is base 16. You just need to be aware of that. So it goes from 0 to F. Okay, 0 to F. Okay, so for now, IPv4 and IPv6 work in parallel. They can coexist with each other, but in future all networks will have to move over to IPv6 because there are no IPv4 left. No IPv4 network addresses left. So we have these numbers, but we need to link them to google.com. So that 74 dot whatever it was, we need to link that to google.com, the name, the host name, google.com. So we use the domain name system to do that. So the domain name system, or domain name service, often referred to as DNS, is a kind of address book. So when you need to find, so when you type in google.com into your browser, that browser will access a DNS system. So to find out, well, where does google.com live? What IP address does it have? The DNS sends back, well, google.com sits at 74 dot blah 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 blah. Your computer goes great, and then goes off to that IP address. Okay. So you'll recognise some of these: .com, .edu, .gov, .net, .org. These are top-level domains. Okay. When we move into country-based, these are the top-level domains. So you'll be aware of .com.au. The .au is the top-level domain, not the .com at that point. When the address is just .com, so google.com, the .com is the top-level address. Just bear that in mind. So domain name system, distributed system for managing host name resolution. Basically, it's an address book, and you have DNS servers, domain name servers, which is a computer that sits there translating host names such as google.com, scbc.wa.edu.au into an IP address. So the internet has 13 of these DNS servers. They contain the whole of the internet IP addresses and domain host names. That's not to say every time you type in google.com that server gets access to find out where google.com is, because actually your ISP has a DNS server, and maybe even your school has a DNS server, which in this case our school does have a DNS server. So when you type in google.com, it doesn't go off to one of those 13 DNS servers. It actually goes to our local server that's sitting in the room not too far away, and goes, that server goes, yeah, google.com, that's the IP address, off you go, and your computer goes off to that. Okay, final slide, very briefly, cloud computing. You might have heard this before. So it's basically virtual networks in the cloud or on the internet that you can access and save and store resources on. So the more common ones that you use currently is Gmail. Sorry, so Gmail stores your email in the cloud. It's cloud computing. Maybe you use Dropbox to store your files and share them. That again is cloud storage, and you're using cloud computing there. So that's very briefly what cloud computing is. Yep, and they are done.